Nice to see everyone again. First of all, I want to acknowledge those who sent me greetings. I really appreciate it. Like I mentioned last time, I have been not very well and also under some extreme conditions. But I believe I will win. As people say, the first step to win is to believe you will win. So that's my belief. And the quality for teaching will not be compromised because I made a commitment to deliver the best to my capability. So that's why I'm here, despite that today is a national holiday in the Netherlands, and also I'm not well, I'm still with you. I'm also glad you are with me. And because there's some imperfect situation I'm in, I also ask for you to bear with me for the imperfection in my lecture notes and the related talks, because I was a little rushed last time. So I will go over some concept that wasn't clear last time. So that's number 1 point. Number 2 point is, as you see, for those people who are careful, I changed my shirt. This is a good reason. There was a story back in Caltech when people study theoretical physics, which was quite a difficult subject. I wouldn't say it's the most difficult. It's fairly difficult. There were students go to class, they didn't quite catch something in the beginning because the subject so difficult. They end up doing is just trying to pay attention to the tie the professor wore on that day. And turn out the professor would change his tie every time to go to class. So the result of that is the students just have something to focus for each class, and they keep until the end. So many of them succeeded. So following the same philosophy, I changed my shirt, or I don't have a tie. So I give you something you can focus on. And in the same light, I also updated the lecture notes, for the last lecture on Tuesday. When I did it together with you, we used a chalk and board, but I typed up everything. So you can compare my notes with your notes just for reference. It's under IC data. You can download for your interest. But today we'll continue the same approach. I will do the chalk and board, then I will type out this later after class. So yes, that's number 2. And the third point, some of you also asked a question about methodology. So I just want to redeclare again, if it were not clear in the beginning. So my intention is trying to share with you my way of thinking. It's more about the guidance, the directions, where you look for the direction for solutions. And I believe by this point, you are capable and confident enough to look for packages or some kind of code if you know where the solution will reside in terms of directions. You may feel that I didn't really know quite as much as using a particular tool. I feel a little ignorant. If you feel so, I will say congratulations. In the field of physics, people always say if you feel you don't know anything, you'll achieve the top level, as long as you feel you can derive from the beginning. So that's the purpose of my lecture. All right, that's my little blurb in the beginning. Let's go to the recap from the last lecture. So we introduced several concepts, which I believe are important for today's topic. And I will use a simple graph to cover all the equations we have discussed last time. Just one single graph. For those who like graph better, I hope it will be helpful to you. Yeah, let me just draw this one. I think you can see, right? It's too small. Can you see this? I drew a square, 2 circles, one called A, the other B. There's a little shade, it's an overlapping area, right?
Yes.
So I just use this one graph to demonstrate all the concepts, all the important concepts we have been through in the last time. So we talk about joint probability, right? Which in my notation is such a joint probability between B, A, and B. So how do you calculate? What's on the graph? It's just a shaded area. The shaded area divided by the whole square, which is called sample space. A and B are called events. So the shaded area is a joint area or overlapping area between the two events. The joint probability is just this area divided by whole thing. Okay. Now I'll come to the conditional probability. So the conditional probability is what? Is A conditional on B equals to A joint B divided by B. That's the equation, right? So how do we understand it from graph? The joint A and B is nothing else, just a shaded area. That's the joint. That's the numerator. And denominator, it's B. So it's this area divided by B. So what's different? The difference is you change the concept of your data set, right? Initially, you have both A and B together. We calculate the joint. That's the area divided by these two together. But now you still have the joint, which is still the shaded area, but the denominator change. So in other words, you shrink your sample space into a different one. So that's pretty much the essence of a conditional probability, right? We also talk about a law of a total probability. What is that? Mathematically, we show B equals to this one, the summation of condition probability like this, right? So what this means? How do we understand from the graph? The total probability here, I calculated B. B is here, right? So let's suppose this A, I should have read subscript I because I have many A events. So you just basically divide this A into small pieces. What you did is you put pretty much sum all this small thing that's been repartitioned due to this, you have created so many A events, or if you only one event still works, just this area. So it's just a summation of this shady area piece by piece. So that's a law of total probability, right? The next one is the Bayesian theorem. So this one, I will spend a little effort because it's important. I will use a lot, and I hope you'll be comfortable. So I'll just go a little slow here. Okay, so let's say V of A, based on the Bayesian theorem, it equals to AB, the A, then have summation, and conditional on B, and conditional on A, right? So what this means, if you look at the denominator, I mean, the numerator, denominator, what is this? This is pretty much a law of total probability, right? You calculate this one, it's pretty much the probability of A. And this one is a rewrite of a joint probability. Aha, you see, the Bayesian theorem is nothing secret. It's just a rewrite of a conditional probability. So that's actually one of the homework I trying to put in our lecture last night actually to work out. But at least you see now, this Bayesian probability is looking scary in the beginning, but if you break down, it's pretty much as here. You can use the same graph to demonstrate. So what's saying here is B conditional on A, once again, the conditional probability, which is this shaded area divided this time instead of B by A, then you partition B into small pieces. So you just use one graph to cover all the theorems. The key I want to point out here is all these relationships are connected. As long as you start from the axiom of probability, you can derive to everything. We write down this as such explicitly for only one purpose. That is convenience. Okay, you get familiar with this one, familiar with this one. Then when you get into more complex derivations, it becomes easier, handy for you to work out. You don't have to go from beginning from the axiom. Okay, so I hope this is a good illustration of this concept we did last time. Anybody has questions at this point? No? Okay. Now I'm going to go to the coin game. I hope you guys enjoyed it. Before I start, I just want to ask anybody work out the problem. You know, we already did quite a lot. I mean, we already got into the bulk and the core part of it. Okay, so since nobody has done anything, I mean, it's also part of my fault. I was a little rushed last time that I didn't explain probably perfectly. So let's just do it again one more time. Just let me write down this small table as we did the last time. Okay, this is the game. I have 2 coins, right? Okay, suppose one from you, one from me. So I put it in my hand. All right, each coin has 2 sides. I will agree on that, 2 sides, okay? One's head, one's tail. The one in my hand, I know when it's going to be head or tail. The one from your hand, you also know it's tail or head, right? So we come to the table of game. We put our hands together, closed. Don't tell each other what is this, you know, it's head or tail. Then we open, then we compare, right? If mine the same as yours is a head, you gain $3. If mine the same as yours is tail and tail, you gain $1. If I have head, you have tail, or I have tail, you have head, you lose $2 to me. So that's the game. So we do this repetitively. Let's make agreement. We do 100 times. Now I ask you, is there a strategy I can deploy that I'm guaranteed to win, right? So this is the concept of mathematical expectation. So we already set up this one last time. Where's my chalk? Okay, right here. We say the probability of head from you, just for sake of notation, is X. The probability of head of me is Y, right? Then we calculate the expectation of you equals to what? I mean, I just want to repeat, I just read the result because we did this last time already. 8x minus 3, y minus 3x plus 1. Okay, this is the end result. So if I win, that means over long term, I expect to be positive, and your expectation should be negative, right? That means this value should be smaller than 0. But apparently you see here, it's not only me and Y, you are X. You also play a role, right? But there's a trick here. If you look at the situation, I will make this one smaller than 0. We have to discuss what kind of strategy you may play, right? Because you know what kind of probability you put with your X. So what you have? You have 2 conditions. One is when X greater than 3 over 8. The reason I want to put 3 over 8 is I want to see if this term in front of Y is greater than 0 or less than 0. Because based on the principle for inequality, if I move this term to the right and then divide this term by this 8x minus 3, the direction of this inequality design depends on the sign of this number. Okay, so if it's greater than 8/3, that means this is positive. And positive means this wouldn't change the sign. So that means this y should be smaller than 3x minus 1, 8x minus 3. Right? So that's going to be the expectation for y. Now, if you look at this function, what is the property of this function? It's a decreasing function, right? So how do you know that? This one, you take the first derivative equal to some square term minus 1. This is b smaller than 0. So when this function is smaller than 0, it means it has extreme values. So if I want to this value smaller than this function, which is decreasing, so I should be smaller than the smallest. And the smallest corresponds to the biggest. That means x equal to 1. So you put it in here, that's going to be 2/5. So that's saying if I have this condition, I should choose my strategy smaller than 2/5. So similarly, if I say x smaller than 3/8, I don't want to show the duration anymore. I can find the same condition, which is y greater than 3x minus 1 divided by 8x minus 3. That's use the same thing if I'm 1/3. So what it means? That means if I choose my strategy, which is the probability to show head in my game, that's in the range of 1/3 and 2/5. Your expectation value is going to be smaller than 0. So it doesn't matter how you play your strategy. I have a strategy that I'm going to win for sure. So I hope you have enjoyed this one just by the superficial level. But I want to take one step further to help the thinking process. So why? Why I can do this? Why I can find the strategy that I'm going to win, on this board, which is appear to be a fair game, right? If we're the same, the amount of lose and the amount of gain is the same. The summation is the same. Why I can do that? Why you cannot find a strategy that you're going to win? I mean, I tell you, you cannot. You can try by yourself, but you cannot. Why? Think about this. Okay, to help you, let's draw another table. Same table, same here. I have head, tail, head, tail. I put this everything's 2. Yeah, this is even more fair. It doesn't matter what you do. I gain $2, you gain $2. I lose $2, you gain $2. So how would that change the game? Anybody want to try? Okay, just for the sake of time, but I hope you will write down by yourself when you have time. I'll tell the result. So same expectation value of u in this table. Now this one. What do you get? You got 4x minus 2 times y minus 2x plus 1. Anybody notice something interesting here? Look, this term on this term. If I set 2x minus 1 equal to c, a constant, doesn't matter what. So I'll write this one should be 2cy minus c. Or in other words, is 2c y minus 1, half y minus 1. So that's correct. Yeah, 2y minus 1, sorry. Because there's only one c here. So yes, c is constant, 2y minus 1. Yeah, so what happened? C is a constant. The strategy view disappeared. Remember, we had x, in the previous game. Now we don't have anymore. So what it means? This means I only have a strategy I can play, and my game is 2y minus 1 smaller than 0. What it means? That means y is smaller than 1/2. Right? If I want to achieve this y smaller than 1/2, I have to make sure y is greater than 1/2, because the probability I can set up here, it depends on the if I y minus 1, that means this one's, yes, this y smaller than 1/2. But I can do the same. If I want to argue I want to greater than 0, that means y greater than 1/2. So the only thing I can achieve, so this is a contradiction. You cannot achieve either. The only thing I can achieve is y equal to 1/2. What is y equal to 1/2? It's a random, throw. So what happened here? Because we have equal distribution here, we have equal opportunity, or we have highest level of uncertainty in playing strategies. So if we lay out in this way, there's no winner. It's all by chance. But if we lay out this way, I'm going to win because my strategy has equal numbers in the off-diagonal elements. If I want to elevate this one, just one step up, that's the significance from statistics. This is the mathematical proof that equality presents opportunity in a society. Okay, if you want to have more opportunity, you should provide equality, because I give equal opportunity for this probability. As long as you play in whatever way to shift this weight, you constrain yourself. Your information get more certain. That's why you have a less opportunity to know one. I don't know anybody's here from social science or not. I hope people can appreciate this mathematical proof to support the social equality. If I have done a good job here, do I deserve a full round of applause? Nobody? Okay, thanks so much. But this toy example, it has a far-reaching consequences. The reason I bring up here is in today, we talk about species distribution modeling. It has something very deep into the basic concept about information. We'll go there and I'll look back when we get there, okay? So now, I'm going to talk one more time about this Bayesian theorem, which using an example to connect the concept of expectation and probability and Bayesian theorem. Okay, so are you with this one? Okay, so this problem is very famous. Okay, it went back to the days when Laplace started thinking about this idea of Bayesian. So it's called the problem of sunrise. So I want to ask you to calculate the probability you will see the sun rising tomorrow. It's kind of astonishing, isn't it? Do you think that's actually a question or not? Well, but actually it's a question. It's a very interesting question. So how do we think about this question? I think you probably will say, based on your experience, every day the sun came out and the sun don't come out tomorrow. That's probably more or less your response, right? But let's put this in a more mathematical framework to think about this question. So, okay, we have been, I don't know, our human civilization, we start observing the stars in the sky, let's say conservatively 5,000 years. We have seen the sun coming out 5,000 years. But does the 5,000 years experience guaranteeing that tomorrow the sun will also come out? isn't it? Because we don't know, right? It's a probability question. So that's also, you know, two schools of thought. So if you coming from the frequentist, you ask, okay, the probability of a sun coming out tomorrow is actually a question of estimation of the best probability for this particular phenomenon. So you can think this is like a flipping a coin, right? Today the sun come out or not, it's like a flipping a coin. Now when we, I'm sorry, there's somebody calling the door. I'm sorry, just 1 second. I mean. Because it's holiday today, I don't know.
This meeting is being recorded.
The real story here, so I just leave it for the moment. Okay, so I said it's a game like a flipping a coin, but it's not precisely flipping a coin, because when we say flip a coin, we say this the coin will land on either side with equal likelihood, right? But it doesn't have to be in that way. Maybe you manufacture this coin in a certain way, one side is heavier than the other, so you always see the head will land when you flip it. So that's what I just say is it's about an experiment. It's a random experiment with a coin that you don't know the likelihood how it will end. So the probability is not 1/2. So if we don't know, we have to estimate this probability, right? So the way to estimate this probability is pretty much using a binomial distribution. We talked about binomial last time. So what is binomial? The P probably mass function of a binomial. If I have n trials of k, that's equal to probability. Yeah, k and 1 minus p times n minus k. So that's a probability function, right? So let's say I observe this the sun for 5,000 years. That means 5,000 years. And see the sun arise every day. That's also 5,000 years. That means k also 5,000. So that's one of the probability function, right? But the thing we don't know here is p. It's a probability. That's our interest. So what's the probability the sun will come out? So the way to calculate this one is using people, you know, in statistics mostly using is so-called maximum likelihood estimator. So this is going to be a little complex, but I'll just put a simple function version here. If you don't want to follow this math part, but you can Google it. You know, Wikipedia is everywhere. It's pretty much equal to, yeah. Oh, I take out the log. So it's probably it's take the logarithm. It's a natural log of this one. It's going to be a constant times k ln p plus n minus k ln minus p. So this is the likelihood function. To make this one, you know, we want to get out something from p. So what do? We say, okay, the reason we see the sun comes out over 5,000 years is because it's most likely the sun will come out in the 5,000 years. So we have to maximize this likelihood, right? To maximize it, it's going to be take the first derivative of this one equal to 0. Okay, when it's 0, then you got this p equals to k minus n, which is 5,000 divided by 5,000 equals to 1. Yeah, like somebody said, tomorrow the sun will come out for sure. That's probability. That's frequencies perspective, frequencies. A Bayesian says, I mean, actually Laplace said, well, it's not entirely true, right? If you look at this one from the Bayesian perspective, remember we talked about Bayesian theorem. So we have a function here. we want to calculate this P condition on N and K, right? Because this probability is the sun coming out tomorrow. We don't know. The only thing we know is we have 5,000 years observations, and 5,000 years the sun comes out every day, right? How to calculate this one? We have Bayesian theorem. I don't want to write down anymore. It's going to be integral something and something upstairs. And the result, this one is a little messy, but good part is if you look at the expectation of this value, you see, we integrating out, you get this result. So it's k plus 1 over n plus 2. So what it means, that means the probability of the sun will come out tomorrow is 5,001 divided by 5,002. It's very close to 1, but it's not 1. So you see the difference. What's the difference here? It's quite important. What is the Bayesian school is trying to introduce here? So in the frequencies perspective, I treat this P probability as a parameter. It's a fixed entity in statistics. It's something we're going to pursue, right? We want to figure out what's this based on our belief. I mean, there's no reason that, you know, the sun has been out 5,000 years. That's the probability is most likely. It's nobody guaranteed, but that's the only thing we can leverage on. But Bayesian came out saying, well, actually, I don't want to do that because we don't know the P. The P is not only a probability, it's also a distribution. So the parameter P itself has a distribution function. And based on the Bayesian theorem, we can estimate the distribution function of P, and then we can calculate the expectation value. So in other words, there are a lot of probability out there for the sun to come out. Okay, they could be 1, could be 0, could be 0.1, could be 5, there's a distribution. But with our evidence in the past 5,000 years, we applied theorem, we got out the expected value, expectation value of this probability comes out to be number very close to 1. So I hope it's kind of explained, but the key point is the Bayesian theorem has treated the problem differently and used the concept of posterior probability to update of our knowledge as we collect more data. It fits very well into the framework of our data science because we keep collecting data and we continue adding new data into our model, and that will change the evidence, will update the post probability, will change the predicted outcome. So that's more or less, I would like to say today about a recap of our previous lecture. And in the next 2 legs, I will cover 2 topics. In the middle, I'll talk about the spatial statistics, because you are all familiar with conventional statistics, and spatial statistics is something a little different. So I'll talk about that one. And depending on how far we progress, and hopefully we have some discussions because I've been talking too much. And the last one, I'll talk about species distribution model. So now I finish my part. I will just leave this open for anybody in case have a debate, questions. I'll be happy to talk with you. I'll be more than happy if you have a debate. So that's how actually the conversation goes and how the thinking process is being developed. Anybody may have questions or thoughts to share?
Yes, Longzhu. So from from a documentation point of view, in the field of remote sensing, for example, the maximum likelihood classification has been used as a first technique to make inland cover. So it's really one of the first starting to apply, probably from the 80 with the launch of for Landsat dataset, and has been carried over for several years, let's say until the machine learning will start to kick in. Okay, with beginning with the support vector machine, and then later on with classification tree, and then neural network, and a random forest, but really the maximum likelihood has been the first one to use it in the in the remote sensing application, and probably also in species distribution modeling. So maybe some of you guys have a more experience in this. Please feel free to say something in this regard if you have experience on this.
Or if something is not clear, whatever you want to ask me. I mean, the mathematical part is not so important. The important part is the concept. All right, I see most people are still staring at the board. I will leave this one so we can have a break, and we come back at the next exact hour.
Actually, I do have a question.
Yes, please.
Yeah, so in Bayesian inference, you should have a way to also include some like a priori knowledge, right? So for example, if you do have some knowledge about the phenomena besides pure evidence, right?
Yeah.
Like, which in this case is the number of Ks and K, basically, right? So how would that change the formula if you had, for example, more evidence? Like, for example, other variables. Let's say that you have like a multivariable Bayesian inference system.
Yeah, good question. Okay, in this example, actually, I didn't write down this thing explicitly. If you write down this part in upstairs explicitly, it's basically the nk by p and fp, right? So this is actually likely to function. So we already used the knowledge of over the past 5,000 years as an inference to estimate the posterior probability. So in this part, we already included. Of course, with new evidence, with new data, we should keep updating this posterior probability. Actually, this one I'm going to illustrate in the next part of my lecture. So hopefully that will make it self-evident how we view this particular subject from the Bayesian perspective. In particular, using new evidence to update the posterior probability.
Right. My question was actually based on like having more variables besides just the pure observation, you know. So for example, in this case, what you're saying there is basically like out of 5,000 years, right? I observed that the sun came up in the next day 5,000 times, basically, right? So like I was wondering, like in this case, it's a little complicated, but like let's say that in some case I do have more variables besides the pure evidence, you know. So I was just wondering if there is a way to do exactly the same analysis Bayesian inference, but for more than one simple variable, which should be just the evidence. You see what I mean?
Yeah. I think if I understand correctly, you're saying, okay, this is too simple case. We only have 1, 2 parameters. If you have so many parameters, yes. So basically, at a high level is the Bayesian model can be viewed as a joint distribution of your process, your data, and your parameter. So the overall updating process is kind of cascading. So you update the posterior probability based on the previous one. You have previous data, previous parameter, previous variable, whatever. When you have more, you keep updating in the basically the expansion of the joint probability. When you have more parameters, you have more individual terms in your joint probability. You just keep cascading and expand. I think when I have this one on the board in the next leg, maybe that will make it a little more clear.
I see. So basically the functional change should be like P given N and K, you just have more variables there. So it would be N, K, F, and whatever.
Yeah. Or have more
okay.
Yeah, I mean that normally we do. You know, this is going to be can be 1,000 parameters, 1,000 variables. That's all the case.
Okay, but then the formula for the expectation should be updated as well, right? So how would that change the formula of the expectation? Because I think that's just for like given the number of observations out of the number of trials that you had, right?
Yeah, well, this one is basically expectation of P, right? P is a probability function. It has its own distribution. So this one is pretty much expectation of this particular probability distribution function. So because I only care about this particular P, I calculate the expectation. Now, if you say you have so many different parameters, then you have asked, what kind of expectation you talk about? It's conditional expectation, it's joint expectation, or it's just expectation by itself. It's marginal expectation. So it depends on how you formulate the question, right?
Okay, thank you.
Yeah, good. We break now. About the spatial stats data.
This meeting is being recorded.
But just before I go in there, I want to have a chat with you about your feeling now. I mean, I assume you are familiar with the conventional statistics, common distributions, linear regression methodologies, and etc. Does people want to say something about so far regarding the statistics? You feel everything, you got it, making sense, or is not in the right direction, or you want to ask for something, you hope for something? Any people want to provide some feedbacks? Do you like the game? You understand the game?
I have a question about that one.
Okay.
For example, if you would do a graph of how the two cases will look like the heads and tails being 2 and 2, and the other case where you have like the losing statistic, how would that graph look like, the distribution of the trials? Would that change, or it would look like similar?
The graphs, when I didn't, so yeah, the distribution, or yes, okay. So basically, yeah, it's a little more than just, if you think this result of you giving head or tail is totally like a binomial process, a distribution, right? You have a probability. But here the key is you have a human control, because we play game together. You know which one you're going to put in there, right? You can keep changing, you can adjusting. So in other words, this is a good example, because if you still think this is like a binomial process, the only difference is the P is constantly updating. This time maybe you put head next to the tail, because you also gauge, when we play, we say we play 1,100 rounds, around 50, you see all things changing, you want to adjust, then you adjust P. So this is like a moving dynamic process. So it's more like a stochastic process instead of just a distribution. So if you think this problem, to understand it, to appreciate why there's such a caveat that I can play in that very narrow band to secure the winning case for myself, it's pretty much, as I said again, is because the opportunity or the uncertainty is higher. Okay, once more, if I have this small table here, head, tail, when we have -2, -2, so that's my strategy, right? So what that means no matter what, I mean, it's a symmetric table, right? It's a symmetric table. So my diagonal and your diagonal different. That's the only difference between us. So your diagonal difference is because you have a different weight on different scenarios. So that means you have put more certainty in your case, and I have less certainty. So I have more mobility. So I have more strategies to play, and I'm more agile. And you are less, so that I can target you better. Because if you think this, once you know the position, you don't know the momentum, you know the position. It's like you have more information you left for me to leverage on, but I don't give you much. I give you nothing. That's the maximum probability I can give. So if you look from me, from your angle, I'm like a totally a mist, a cloud. I have no knowledge. But if I look from my perspective of your position, I say, oh, I don't know everything. You still play strategies, but you're more or less, maybe next time you're moving more like here, more like that. I have a little more probability to make predictions. So that's why I'm trying to advocate, equality is a really valuable scenario. Okay. Just work out the mathematics. You will see just from pure math, you understand. Hopefully, why that's the case, I can play to win.
Okay.
Yeah, I hope I explained a bit. You have to go through this one a little bit. This is like a general scenario for. Yeah.
It's interesting. I need to like read some of the content that you uploaded, but this one is an interesting case.
Yeah, if the derivation, it's very simple. This is a high school mathematics. It's nothing really special. The only concept new here is the mathematical expectation. If you look at my node and follow all derivations, you can see clearly just by numbers, I have a chance to win. So that's the easy part. In physics, people say, stay with mathematics because it's easy. Then everything else, if you start thinking, it'll hurt your brain because it's getting more complicated. But this one, it ties to the information theory. Basically tells you how much information you have so you can make predictions, and the less information you have, the less probability you can deploy strategies. Okay. But it's a fun game. I hope you can get more out of it. And also it ties to one of the model we can talk about in the last part of class for the species distribution. So that's all about, the mathematical models. It's from simple things, very simple toy examples, and you can extrapolate to bigger and more complex scenarios. All right, so that's my little blurb. If people have more questions, please feel free to jump in. If not, I will change the gear to talk about spatial statistics. All right. So let's get some notation down here so that people know what I'm talking about, because I will use notation later on in the species distribution model and also the analysis. Okay, so in general, in spatial statistics, we have such a notation, Z as a function for S. So Z is a random variable. It could be, a species occurrence. It could be a precipitation. It could be NDVI. It could be anything that's geologically, geographically interesting. And S is a location. And this location varies over an index set, which is D. So I put a D here because we're talking about spatial process instead of temporal process. So D is pretty much domain in space, whatever you want to use it, like longitude, latitude, degree, whatever. So in other words, this particular observation you get from a field is represented as a function of the particular location where you have obtained this particular observation, right? So one particular feature of spatial data is that spatial data are more or less dependent. In general, I think there's a famous theorem in geoscience is that nearby are more alike. Things are nearby are more like each other. So that's probably the only theorem I know in geoscience. What that means the data in the geo domain are more or less correlated and they depend on each other. Now, at this point of our lecture, I think you already knew where I'm trying to go, right? We talk about dependency already previously in the lectures about the conditional dependency and the independency of data. So we're going to treat dependency in terms of conditional probability. So more specifically, I just gave you an example to illustrate the concept. If I say there's a geo process, it's a Gaussian process, it follows this particular Gaussian distribution with mean equals mu, and the variation is a sigma, which is a n by n matrix when you have a, different data in a matrix. So that's pretty much a simple Gaussian process. But many times in geoscience, we don't say this process by itself. We ask the question of the condition of one particular process on another one, because data are dependent. So if you do this way, you got something like this. And then this is phi, and this is Zi, some operation on Zj. Then you have a coefficient phi square, 1 plus phi square. So it's still a distribution, but you look at your mean value and the variation, variance change. And this particular one equals to the covariance between the process of Zi and Zj. Okay, so that's basically how you see the spatial data deviates from common statistic data, where we apply this concept of IID, which is identical, independent, distributed. So they are normally independent, but here the data in geoscience many times, most times, are dependent. Another example, if this one doesn't really resonate with you, I'll use example from linear model. I think we are familiar with linear model. If I write this linear model, okay, I still use Z, but just ordinary linear model, right? This is just ordinary linear model. What we have is your design matrix and your coefficient obtained. You have a error term. This is for the normal distribution, and your estimate based on regular normal least square. The result is hope this is correct. Oh, it's -1. It's as such. The reason is as such is because this particular term follows Gaussian distribution, and all these columns in this X are independent. But if you put in geoscience, you change this one into a generally square, what you have is you see here, you have more terms. What is this? This is the covariance matrix of your spatial data, because your data are correlated. And this one is not equal to the variance when you have with the conventional data. It's actually it's actually an n by n matrix to characterize the correlation of this data when you have nearby environment. Okay, I just with this example, you don't have to remember details, whatever. The key is you see the formula change. And the reason the formula changes is because you have a correlation. Your off-diagonal elements of your matrix is no longer 0. So that's the key idea. We have dependency, right? So that's more or less about it. So you have a taste about the spatial data. Since if we're going to talk about dependency, we're going to talk about some basic characteristics of spatial data, which is the first moment and second moment of spatial data, which corresponds to strong and weak stationarity.
Longzhu, one question.
Yeah?
When we are making a linear model in the geo environment, and we are getting the residuals.
Yeah.
So if the residuals are still having spatial correlation, means that we are not applying the second formula, correct?
Well, it depends on how you formulate the question. For example, you can use mixed model, linear mixed model.
Linear one. just linear without any stuff.
Yeah. I mean, you can use a linear mixed model, which is also linear model, but instead you have one epsilon, which is just conventional one. You break this into two parts. One just account for the conventional random effect, which still follow the Gaussian distribution. Then you have another part, which is as part of this whole epsilon, which accounts for the correlation between different geolocations. So I will go to there when I get to the mixed model, and you will see.
Okay, thank you, Longzhu.
Yeah. So I'm going to talk about these two characteristics in spatial data. The first one is the expectation. So again, Z is your observation, S is your location, H is kind of distance. You change the distance to go to another location. So if you look at expectation value, this is statistical expectation, and this particular term equals 0. That means the data is stationary. It's strongly stationary because everywhere difference is it's pretty much the same. There's a particular distance. When you go over that distance, you observe the same thing again. So this is the first one. The second one is the variation. Again, you have this one. So the variation of these two locations, also these two locations differ by particular distance is h. You can arrive at a particular function. That's a function is a function with the distance. So if this distance is constant, that means the geodata are weakly stationary. So in other words, that means the variation differ by this particular distance in the geospatial science, and they only differ by this particular distance. There's nothing else in play of this particular phenomenon. And furthermore, this H can have two particular consequences. One is the magnitude, the other one is the direction. So if your function, when you come out where it is, you show this particular dependency of the second moment, so only a function of magnitude. And this one is called isotropic. If it's also dependent on direction, that means anisotropic. And if you have isotropic situations, that means your geodata point is resistant to translation. And if it's if it's anisotropic or isotropic, it means it's resistant to translation. But if it's also isotropic, it's also resistant to rotation. So that means it doesn't matter from which angle you look at data, they always have symmetry in it. All right, so that's pretty much the characteristic of this data. Key point is the spatial data are correlated, and there are ways to characterize the fundamental features of this kind of correlation. And also this particular one in geoscience called the covariagram. You can plot it out to see how this data change over the locations. I think Giuseppe has a question.
Yes, this is pointing the fact that when we talk about variables and correlation in the spatial domain, in the spatial domain, these can be isotropic or what does mean that can change as a function of the direction where we are going. So in other words, for example, if you have some gradient, okay, some gradient in elevation, the temperature will change drastically going down and up in the elevation gradient, but will not change if you go in the other direction. Okay, so this can be correct. So this can be seen if you do it the variogram, and it's something that we will see. That can be a variogram uniformal, so that is looking at all the different variants in the spatial domain, or can be monodirectional in one specific direction. Okay, so this can change in according to the variable that you are looking. Okay, so this is just to point to some specific aspect in geoscience.
Yeah, thanks so much, Seppi, for pointing out. I just want to draw two, simple graphs. So this is the variogram Giuseppe talked about. If you want to plot the variance on y-axis, and this is the distance of h, you see, go gradually away from the point of interest. You may observe kind of linear relationship, or this one, or even kind of sine function, whatever. And all these different characteristics tells you how the geodata, the dependency of geodata played out in your particular case. We can do some more plots when we go into our data, but for the moment, I just cover some high-level concept, which is, I think, it's important because if we don't have this, it's going to be a little confusing when you talk about just the modeling by itself. Okay, so now we talk about Z, right? Z is what? It's data or observations from geoscience. But there are other concept variable. Is Y. It's called process. Right? So what is geoscience? Geoscience is there's a fundamental process to drive the generation of the observations you observe. These observations, no matter is a present for species or natural phenomenon, there's an underlying geo process determines that. And there's also parameter. Right? As Antonio asked in the last part, this is a parameter, it can be value and can be also just vectors. All these are vectors. Okay, so basically our goal, the general high-level overarching goal of geoscience is to do this. Is to estimate the process and the parameter based on data. So we only have data. We got data from the field, and we collect this, environmental variables. We also estimate the distribution or the probability function of your process and your parameters. Then how do we do that? This one equals to Bayesian theorem. Right? So you can cascade this whole process into this one based on Bayesian theorem. And what it's saying is the posterior probability, which is our interest, is proportional to the data model, process model, and the parameter model. Yeah. So that's our goal. So let me just demonstrate. In one instance, actually, that's related to the question Antonio asked about the updating of your model using the Bayesian theorem, right? So let's say you have two group data, Z1, Z2. You can observe Z1 first, and you have observed Z2 because that's going to change your possibility, right? So based on the Bayesian theorem, when you have Z1, the first time you got data, this one, the posterior probability is proportional to right? Yes, that's what it is, right? So you haven't seen Z2, you only have Z1. That's how the posterior probability is going to be. Now with Z2, your estimation change, right? Because you have Z1 and Z2 now. You don't estimate this new posterior probability because you have new data. So we have new data. I don't have enough space here, but yeah, just make it here. I just write down the conclusion. I think you can do the duration by yourself. I hope it's not. I mean, based on everything I said before, you should be able to. Arrive here. I skipped like 2 steps, but you should be able to arrive here. So what is showing here is the new posterior probability has been updated given the new data. Now it's not obvious here because you have this conditional probability, but you can simply multiply this one with Z1 and this one with Z1 here. So what is one give you? Conditional times this one self. It's joined, right? This is one. So if you got the posterior probability, which is still here, is proportional to the new data model. But in new data model, you have information from previous data. A new process model have the new data and have the previous data and the previous data. So if you look at this particular posterior probability and compare to what it was, you see the difference. So that's what it means when you have new data, you're constantly updating the posterior probability. Any confusing here? Okay. Now, apparently this is going to be a little messy, right? If I keep doing this with so many process from data, there's some way to simplify the process. One is the fourth order Markov assumption. So it's also called process model decomposition. Okay. So what it says is if I have many processes, because there are so many of them, is a joint of all the process I have collected. This one should equal to, based on the chain rule of probability expansion. You have this one, y equal to 1, t minus 1, yi times y(t minus 1), condition on joint, y equals 2, t minus 2, yi, until y2 condition on y1 and y1. Right? So if you really want to model this process, it's going to be very complicated. Now, if I apply the fourth order Markov assumption, basically saying, well, I only say the future step only depends on its immediate previous step. In other words, yt conditional on everything. Time equals 1 more t minus 1, yi equals to yt minus 1. So that's it. So with this one, you can simplify the process from upstairs here. This one. Yeah, actually it's everything. Oh, yeah. I just repeated it once more. This one equals to you see, from this expansion all the way to a simple version. So that is the process decomposition. Okay. Now, there are a few caution here when you apply the strategy and the techniques here. Number one is the argument of causality. Okay, so we talk about, we can use this process of decomposition to argue one particular process depending on another one, or we tend to say the process one equals process two, right? But in many cases, you have something called a level of spatial aggregation of factors. So your true process may be a collection of all these parameters, process one, process two, and this also F is a factor. Okay, if you write down this one, basically again using the Bayesian theorem. Yeah. Here. So the real case is actually your y2 is a conditional probability of your y1, also this factor of f. If you interpret this one as this one, then you found the false cause for a particular process. This is pretty much an analogy of the Simpson paradox we talked about last time in the class. So when you have change of support in the spatial data, you tend to ignore this factor of f. Then you just remove this one. You try to interpret the data based on this. So that's a particular danger of spatial process. Another one, also people have done many times in spatial science, that also was mentioning, is instead of looking at the process directly, they calculate the likelihood function like such model. Okay, so instead of calculating the posterior probability of the process depending on data, we only trying to build a model that's the data depend on a particular parameter. Then we estimate parameter, and that's have been done many times in geoscience. And this is called likelihood inference. The problem is it needs the fundamental importance of process, which is rooted in physics, biology, chemistry, economics, and ecology, whatever you name it. So if you want to do this, many times what we do is, because we have so many observation data, we use the tilde, which is smooth version of your data, and you say this is a function of original y, and many times this is just a mean value of different observations. Now, if you really intend to do this, and you try to use this particular model strategy, you miss a lot of the fundamental process of process, and the fundamental concept process. The real calculation for this one should be C tilde this one is proportional to so I differentiate data from data versus process, two different parameters, because you can estimate parameters from data and also can estimate parameters from process. Now, if you want to actually write out this one, you should use the marginal probability, which is write out this data as an integral of it's a little messy here. I'll just read out. So this particular probability of your tilted data depends on parameters. It's pretty much a marginal distribution if you integrate out the data model along the process. Now, if you do that, you inevitably have invoked the recognition of process, which you don't know. So this becomes an impossible task from the spatial perspective. So this is pretty much high level of statistical data and modeling. I probably know, I also have feeling you feel it didn't really grounded to a particular applications. That's why I prepared the material for the spatial modeling for species distribution, so that you can project back the concept I'm going to introduce shortly to this big picture I mentioned right now. Okay, so I'm going to move on to the next topic. I want to pause here in case anybody has questions.
Yeah, I think it will be more clear this mathematical step when we see the study case, Longzhu.
Yeah.
So we can please refer back to them when you are explaining the study case.
Yeah. Okay. Yeah. So I will. I mean, I just want to. Yeah. Okay. Thanks so much, Seppi. That's very good suggestion. I just want to say, there are several quotients at high level when you build statistics data. Spatial statistic modeling. So I just lay out all the key points here, and the key message to take home is the spatial data are normally dependent. The way to treat dependency is using conditional probability, and that many times translated into the variance covariance matrix have non-zero off-diagonal elements. And the true process of this modeling requires the data to update information to have a better estimate of your process. And many times in real practice, we just rely on this process decomposition to simplify the process. And one particular potential error-prone approach is to ignore the change of support, which causes the wrong causality. And the other one is using smooth function of data and trying to integrate out this process actually cannot be integrated out. So let me just go to the spatial ecology part for the species distribution model, where you can see some real examples. And where we encounter this idea again, I will highlight what I mean by that. Okay, so I will start with spatial ecology modeling. Just a word of warning, I know not every one of you are doing species distribution models. I know that. I picked this particular one because, first of all, some of you demonstrate interest on this subject. And apparently, I'm also interested in, spatial economics or slide modeling, many different subjects. If you may have interest to discuss any particular thematic modeling, we can also do it during the material time. And for the moment, I only prepare this one as an example. And I think it's simple enough and for everyone to understand. And also, it reflects a lot of basic concepts in spatial modeling. So I'll kick off by quoting Ronald Fisher's famous quote that statisticians cannot evade their responsibilities for understanding the processes they apply or recommend. So that basically means understanding the fundamental process of your particular domain is crucially important, especially for many of you sitting on a huge pile and rich domain knowledge that's extremely valuable. And I also made my best attempt to understand community ecology before performing any model. So I hope I say things correctly because I'm not real trained as an ecologist. I'm happy to discuss with you when I go along. Probably you have some complementary views to support. Please feel free to kick off a discussion or debate anytime. I'm eager to hear new ideas and new perspectives because as I read this material, I found it quite interesting. I feel more confident to speak from the perspective of mathematical biology, the ecology, but I see some overlapping between two different fields. Okay, so let's start with this biodiversity. So I think there's a particular person called Whitaker. He proposed a law called the law of multiplication of diversity. He's saying this gamma diversity equals to alpha diversity times beta diversity, which respectively refers to the total number of species in a particular environment and the average number of species in a particular location and the variation of species composition between locations. Now, I think by now, people still have interest to understand and analyze this parameter beta. And also because of that, it drove and stimulate the popularity of community ecology. So basically two process, or two concepts underpin the community ecology. One is organism concept, the other one is individualistic concept. So the previous one claimed that the traits of the collective species determines their presence. And the later one, the individual one, claims it's not the trait, but the specific species response to the environment determines its persistence. I think the debate is probably still on. I don't know which one is winning or not, or I don't want to take a particular decision. I just want to demonstrate some, based on my understanding, the key interest in this particular field. All right, so after that, I think Giuseppe already mentioned there's a niche theory from Huntington, and he mentioned this concept of a n-dimensional hypervolume, which is the determines the resource and the environment that determines the presence of particular species. I believe it's still being used in the niche theory. And of course, there's some criticism about this particular definition because sometimes it's hard to define. Different practitioners find different niches, and the species impact on the environment versus the environment impact on species is hard to distinguish. And eventually, there's also competing theory from MacArthur and Wilson. It's a famous equilibrium theory of island biogeography, where he says the number of species is pretty much balanced on island by immigration and extinction. So this is quite a good example because he has done an experiment on different islands, bigger ones, smaller one, and he found this theory is good supported in different experiments. And that led to about 2000, the last year, I mean, not last year, the last century, the unified neutralized theory of biodiversity. So where the claim is the diversity arises and organized at random. So all individuals are ecologically identical, and there's no need to implement the concept of niche to differentiate their diversity. The stochastic process, including birth, death, migration, and speciation, totally determine the occurrence of species. So I would like to just hold my talk here because I realize we are reaching the time point of break. I have one more theory to discuss in the later part, but I want to have a break right now, and then we can have a discussion for the very last leg of the lecture. And I hope I get some feedback from you regarding the different theories. All right, I conclude my talk. We come back in the next exact hour.
You are mute, Longzhu.
Can you hear me now?
Yes.
Okay, perfect. So I talk a lot about history and theory in ecology. I didn't tend to just lecture on this. Just want to show you my personal perspective. Actually, my favorite one is one I put up here. It's called the theory of ecology community. So in this theory, based on my understanding, there are 4 major components: selection, drift, dispersal, and speciation. And they correspond to, respectively, fitness, random, movement, and variation. So you can see, my interpretation here is to form a particular ecological community. There are different forces that have play in this particular situation. Fitness is more or less a deterministic process to determine the fitness of particular individuals to the environment and to probably interaction with other species. Drift is completely random process. Movement, there's a migration, the species through different environments. And speciation is increase the variation in particular set. So all these you see that they all have a good counterpart in the theory of a random process, stochastic process, and statistics. So I feel I personally quite like this one. But I know many of you are ecologists, including Giuseppe. I don't know, somebody want to say something about their theories, their understandings, because I feel we are doing models, we have data, we want to build a particular representation of our data and trying to make some claims on correlations. But ultimately, we want to ask a question, a good question in ecology, right? And that question has to be rooted in some ecological theories. Does anybody want to share about their thoughts or their individual perspectives about the theory in ecology or species modeling or some other discussions?
Yes, Longzhu, I jump into it on these topics. We are mainly, or at least when we were teaching in other scenarios, or even in a project that I'm developing right now, we are doing species distribution modeling with the presence-absence situation. So I think, and I will try to read in which one of these the presence-absence scenario in one of the 4 points that you have been listed fell into it.
Well, it's a good question. I think present absence is only one particular case in species modeling, right? So when you say presence, that's also a counting. It's also number. So when you say present and absence, it's kind of a simplified version of this particular situation. If you include the number count, of course, the movement and the randomness all included. And also when you talk about this the spatial species modeling, you talk about a projection or correlation between the presence of species and the environment. Then I ask question, in an environment, it's not only one species, right? There are also other species. So the function is not only this present species correlated with the environment, it also has to include interaction with other species. That's why you have selection, you have movement, you also have drift speciation. So all these ones have roles in play depending on how complex model you achieve. And also I think that bring a good point to our topic of species distribution model, right? So there are 2 kinds of models. One is correlative model, the other mechanistic model. Correlative model, the goal is pretty much, we have a bunch of environmental variables, you have absent presence or counting species data, you just build a correlation. And that's more or less your goal. Maybe you wrap it around with a little interpretation. And the other school is called pretty much mechanistic models. Basically, you build this model, then you look back into the theory to see if this particular model support or refute your theory. Then you can further advance your theory. So that's why I try to say repetitively that understanding the fundamental process is critically important in species modeling, but not only species modeling, in all kinds of modeling, chemistry, biology, everything. So given our time and setup, we probably cannot go so much into the mechanistic modeling because I'm not an ecologist. Maybe we'll talk a little more about correlative, but if any of you have insight and present, I'm happy to learn from you. But just one word of warning in terms when people do these correlative models is that we are having a strong tendency to expand the space of predictors, and the result of that will be the advancement of the model complexity. And in the end, it tends to overfit. And that's not only make the interpretation model more difficult, and also makes the modeling exercise pretty much like a data fitting. So the recommended approach in the society is pretty much variable selection. Variable selection based on their ecological relevance. All right, so that's more or less my blur for the theory. I really like these topics. I'll really enjoy if somebody want to talk about some other theories or their input. If not, I go into some typical examples of modeling in species distribution with emphasis on correlation. All right, let me just erase the board so we have a new fresh start. Okay, so let's start with simple. The simple is species modeling, where I only consider the presence of species is pretty much prescribed by its environment. So if I write a general or common linear regression function, where Giuseppe mentioned already in the past, and I will bring back again to what I talk about notation, which is the data, is pretty much can be written in such a yeah. So the reason I don't have this because I have this expectation value. Okay. So if you remove expectation value, you have the error term. When you don't have the term, then you have to specify this z follows this particular distribution, which is normal. So this is your regular linear regression, and we do all the times. And this one doesn't consider the spatial correlation and requires your observations follows normal distribution. And also expect this error term, which you have here, also follows normal distribution. And your data variables should be independent. That's the basic concept of building model, is trying to look for a particular representation in the span of your design matrix. And the span of design matrix is only well defined. You have a full rank of this particular matrix. I think we already talked about this, in the conditioning part. So just want to refresh some memory what I'm talking here. So apparently this is not particularly useful in many cases if you have only presence and absence data, as Giuseppe mentioned. So that's why you go from here to the general linear model, where you have a function of z built by a link function and present this kind of relationship, right? And this link function have several options. It can be identity. If the identity is just a normal linear model. But if you only have presence and absence data, which is 0 and 1, apparently it doesn't follow normal distribution. And also, you cannot really model the likelihood from this general regular regression easily. So what's our strategy? We build a link function. What is the link function for general linear model for present and absence data? It's a logit function, right? We call it logit. What is the logit function? It's a ratio of the probabilities of you observe a particular species and take log. It's too crowded. Let me just rewrite this one. So what's the benefit of doing this? So when you do these particular operations, you can calculate the inverse function of logit, right? What's the inverse function of this one? Right? What this means? This is a probability interpretation of your particular observation. It tells you the probability to observe a particular species. Okay, so this is the logit function we use for presence and absence data. Then how about we have a count data? Instead of 0 and 1, we have numbers. We have different numbers of observations. Which link function do we use? We use the Poisson distribution, right? We take log. You take log, you got the Poisson distribution, which is accounting to the count. So that's pretty much the general strategies in the linear framework when you consider the absence and presence or count data in species distribution model. But there's one particular thing I haven't mentioned yet, and you should have asked about spatial correlation, right? What happens if data are spatial correlated? I mean, they normally are spatially correlated. What kind of strategy we can implement to consider spatial correlation? There's something called linear mixed model, right? Linear mixed model, where you separate the fixed and the random effect in your explanation. So basically what it does is like if I draw a grid of your sampling data, like a forest, maybe you have several points here, and points here, point here, more points here, right? So you partition your observation space into this kind of grid, then you call each of this one P, a particular area, just a P. Then you write down this particular observation data. It equals to the summations xi, hi. This is the original one, the same as before. Then plus alpha plus epsilon. Actually, it should be alpha p because it depends on which p you're talking about. So what are we talking about here? We have two different residuals, right? One is epsilon, one is alpha. And alpha follows distribution, epsilon follows normal distribution. So what it does is separate the effect of the spatial correlation and the pure residual or random. So it's a fixed effect versus a random effect. So how do we look at this? So if we say residual, right? We calculate residual, the expectation value of this one should be 0. And the variation of a residual should be equals to these two variables from your model. One is from the random effect, one from fixed effect. And how do we translate this one into our variance covariance matrix? That means if your data are sampled from same plot we have here, right? If it's the same plot, that is your covariance. Yeah. Ij. If it's from the same, I have correlation because I'm the same area. There's some correlation. If they come from different, equal to 0, there's no correlation. So this is one simple and quite effective approach to consider spatial correlation. In other words, it splits the original linear model, the residual, into two parts. One is a spatial random effect, and it's a fixed effect. Fixed effect corresponds to the original linear model. Okay. So now I want to talk a little more specifically about this present and absent data, as Giuseppe already mentioned so many times, and so many of you are working on this kind of data. So what's the challenge here? Normally, we talk about presence and absence data. We talk about the obtainability of this kind of data, right? If it's presence, you can go out in the field and collect observations. If there's a bird, you mark down one, you just leave it there. But the challenge comes on this absence, right? So how do you define absence? Let's say you go into this particular area, you didn't see a particular bird, you just say it didn't exist, it's absent. We have two issues right here, right? One is detectability. Maybe you went to in the forest area, it has a very big forage coverage. You didn't see the bird. It's totally because you miss it. Actually, the bird's there. And there's also sample bias because you may have to, sample in a big field. In some area, it's maybe more accessible than others. Then you just go there often, or you can see things better in that area, or different time of the day. You have different climate conditions. You have better visibility. Then you have a better observation outcome. So the absence data is really challenging in terms of the rigorous definition in ecology. Now, is that possible that we can build models just using the presence data? Let's just leave the absence a little bit and we deal with that later. The answer is it's possible. There is something called max count. Model. I think some of you have heard about it, may have used it about it already. So I want to elaborate a little bit on the concept of this model and its application, and then I'll move on to the generation of pseudo absence data and some strategies there to treat different ways account for species absence. So let's start with this motivation, right? So let's say I have a function, probability function for this particular location, right? I want to calculate, my interest is a probability given this location, I observe a particular species. So that's pretty much the conditional probability, right? How do we calculate? Bayesian theorem, right? Bayesian theorem. I hope at this point, you'll feel confident and comfortable with notations. You can use Bayes' theorem to calculate the probability that you observe in a location you have a particular species is pretty much proportional to this conditional probability if you have this particular observation and you see which location it is. This is pretty much a general strategy you want to calculate. But there's something missing here. Is inevitably we have to calculate this one, which is a denominator, which contains both the presence and absence information. So we don't have absence data. We cannot go about it directly. So what do? We estimate the probability function here, right? How do we estimate probability function? It's an unknown quantity, right? We don't know how the probability function looks like, but there is a JS principle which saying when we don't know the distribution of a particular function, then the distribution, we should say the distribution that has the maximum entropy is the most likely distribution we can estimate. So that's the fundamental idea, right? So then what is maximum entropy? What's entropy? So if I say entropy is equal to minus plus x log x, I think that's correct. Yeah. So it's like a summation of the probability function's value and log value. So what is this? It looks like a mathematical expectation, right? It's a mathematical expectation of the logarithm of this particular function, right? So how do we use one? How do we, find a function to maximize this particular expression? So we have looked into the feature space, where we have a lot of environmental variables, elevation, precipitation, everything. So we say we have a collection of feature space F1 to Fn, right? Then we can estimate the expectation in the feature space, which is Fj anyone equals to the sum of pi Fj. So that's by definition of mathematical expectation, right? But when we have features, we can calculate the real mathematical expectation for any feature, right? So we can denote this one as tau tilde. Fj is just the mathematical expectation of the feature. So we should say this estimated probability function should have as much possible, as close as much possible, same expectation between estimated and this tilde value. And then how do we go about this particular function? And there's a theorem to show actually the Gibbs distribution Q lambda equals to exp lambda fx z is equivalent to the unknown expected function, or in other words, the exponential family of functions should qualify for the estimation of this unknown probability distribution. We don't know how it looks like, but we know that's the direction where to look, is exponential family. And then how do we do this? Instead of maximize this one, we can minimize its log value. Then we can apply a regularization, which will regularize this tilde an expectation of L1 norm. Remember we talked about the vector norms for a particular feature. So we do this iteratively. We start with lambda equal to 0 in the beginning, everything, we know nothing. Then gradually, as we iterate, we move downstairs to get this difference as small as possible under constraint. So then we arrive at this maximum outcome, which is maximize the entropy of your likelihood function. So this is the strategy when you only have the presence data.
May
Was it
I
clear?
ask a question?
Sure.
So these features that are defining absence or presence, or generally speaking, the environment, do they need to be equally likely to determine absence or presence? Because we don't observe the absence ones. And if we only select features that predict, let's say, presence, but not absence, is this how this plays here? Thank you.
Yeah, well, good question. So, I mean, I think if you already knew ahead of time which features are relevant to absence and presence, then you already have a very clear-cut picture of your model, right? So in general, one particular feature is a probability distribution function. It has some kind of overlapping with presence, some with absence. So it's an overall effect of multiple features. So I think it's unlikely for a particular feature that is powerful enough. I mean, maybe it's possible in ecology, but it's unlikely the particular feature just can tell them apart. Or it has a particular determinist result. But if it does, there's also argument from the society of maximum extent, because the argument is the information of absence is actually embedded in the information of presence, because it's information theory. So the reason a particular species present in there was because this the absence of, so okay, let me try to do that a bit. So the presence of a particular species in there is because the exclusion of features that will not support this particular presence. So in other words, when you observe a particular species that's in a particular environment, it's actually a combination of information of the presence and absence. So that's basically the argument the author proposed. Of course, there are criticisms for this strategy. It's still in debate. Some people like this idea. Some people don't. Some people say, based on this maximum entropy, the performance model is actually much better than many, general linear models or linear addition models. But also others saying this is fundamentally conceptually incorrect, just using this present data only. But I'm trying to explain from the pure statistical perspective, also my interest, how we understand this model. I hope that answers your question a little bit. All right. So, okay. So now, if we, some reason don't really think this approach is the approach for us, and there are some reasons, like already mentioned, whether this is a good approach, only use this presence data and include the absence data implicitly, or we should consider absence data. Well, if we want to consider absence data, there are actually several strategies to generate so-called pseudo absence data, right? So one thing you can say with this data just totally random. We think that's pseudo absence. The reason is, I believe if I observe the presence of a particular species, there has to be a reason for that. It's not be random reason, it have be something else. Then I can say the background information or the absence data can just only purely generate by random. That's one strategy. Many people use it. And there's also strategy using random with exclusion. So that what it means, you can include the the locations where you have absence. You think if there's absence, there cannot be absence at the same time, which is kind of, statistical debate still have to going on, kind of absence and presence occur at the same time. Or you can weight it based on environment or based on geography. But what I want to point out is no matter what kind of strategy you use, it all boils down to one critical question, which is spatial extent. I think we talked about this before, is the scaling. It's a scaling concept. How to define the boundary between an area you think this should be exclusively considered as presence or occupied area, and beyond this boundary is absence. It's a challenging question. There are some ideas, actually, also Mariam mentioned that about the feature space. Maybe it's possible to analyze the feature space using machine learning algorithm to look at the presence data to see what kind of feature space should look like in this, based on some distance analysis. Then you can just generate the feature space that purely in the complete set, in the complementary set, which means you exclude all the features you think are in support of your presence data. I see, you say, okay, I didn't provide a solution or anything. Actually, there's no solution. People try different strategies. If you don't know, I think a common practice is you can generate pseudo absence data using different approaches and compare the final result and the influence of this result due to the absence data. And then I want to step more to talk about this counting data, which is the Poisson distribution. So Poisson distribution, which is you not only have presence and absence, you also have count. Now let's go about the deer population. You go to observe deer in a forest, you count numbers. It's not only presence or absence. Okay, so your data will be like a column of different numbers, maybe ranging from 0 all the way to a big number, I don't know, 100 or whatever. So the general strategy to do this is using the Poisson distribution. But there's a little caveat here. The caveat is in many times, in many practice, the data we collected, maybe they have too many zeros. Okay, too many zeros is mean too many absence, or we generate too many absence using our pseudo absence approach. And this causes a problem if you apply the models directly, because you will not have enough variability in your model to explain the final outcome if you use the Poisson distribution. So in this particular scenario, you have two strategies. Okay, one thing you can try you can use zero inflated Poisson model. Okay. And the other one, you can use a two-step approach. So the difference, okay, let me explain the zero inflated. Zero inflated is basically you rewrite the Poisson distribution in a way that you have two mechanisms to generate zeros. The Poisson process itself can generate zero. Then you have another formula that can generate at the same time. So basically you have two mechanisms to generate zeros. That's the zero inflated Poisson distribution. Two-step approach is you do present and absence first time. Okay, when you have data, you just convert everything that's not zero into one in step one. So you do a present and absence evaluation. Then you return those values who are one, their original numbers. Whatever number you obtained, you do a Poisson distribution modeling. So the difference between the approach is basically the first one, you count the too many zeros at one shot using one particular formula, and the second one you have two steps. So it comes down to like a more or less personal preference, and there are ups and downs for each approach, but at least there are some strategies out there that's available. Okay, so this is a Poisson model. And lastly, I want to touch basis on so-called joint species distribution model. And by the way, I used the linear or general linear model to explain this species model just for the sake of simplicity. It's easy to explain, to interpret. Of course, you have all the machine learning arsenal you can leverage, like random forest, naive Bayesian or other different strategies to actually to do the species distribution modeling. And actually, in next Tuesday lecture, we use random forest to build a model for tree height. Okay, so just for the sake of simplicity. So now we talk about joint species distribution model. Well, actually, in this species distribution model, yeah. Actually, in this particular case, there are also two strategies. Okay. The reason with the joint, we pretty much want to emphasize there's interaction between species. That's why we consider joint. It's not only the environment itself prescribe the presence of a particular species, and also the inter-interaction between species. So that's the idea. But this kind of interaction can be direct or indirect. So let's say the indirect first, right? Let's say you have you have a patch of grass. You have two different kind of animals, and they all eat grass. They eat the same kind of grass. So they don't eat each other, and they don't interbreed. They don't talk to each other, but they just eat the grass. But because the grass is a sole resources of food, if the population of one particular species is dominating, then the other one will not have enough food. Then they die out. So they don't have a direct interaction between them, but they all compete for the same resources. So in this particular scenario, you can use something like stacked analysis. In other words, you build distribution models as individual species as yourself, as you do linear regression or general linear regression, whatever you like to do, to build their own models as yourself, and then put these two models together as your final prediction outcome. So basically build two models and have additions to models through the resources as a limiting factor. And the other one you build, which is more like the real joint distribution species distribution model, which is considering the interaction between species explicitly. That means you have to change the representation of your observation. Initially, in this observation, you only have one column, right? It's just like it's a vector. So you only have observation of a particular species. Now you have multiple species. So this one will become a matrix. So the matrix will be like this. You have Z1, like Z2, Z3, etc. Then you have many rows, and each row is a particular site, So S1, S2, S3 observations. So your response variable will become a matrix on the right-hand side. So that means you have to write down it's Z equals to XB, right? So initially you only have one particular, if you use the linear model framework, it's easier. Let's stay with the linear model framework. Initially you have beta, right? Beta is a vector, and it's a vector of a coefficient corresponding to each particular observations. Now you have B. B is also a matrix. B has the matrix element of Bij, right? And this J corresponding to different species this corresponding to location, right? So in this approach, you have to use a little different matrix algebra to work out the solution, but that's pretty much the basic idea of a joint species distribution model. I personally think the community ecology should consider the species interactions, and there are multiple strategies to consider species interactions. I think there are famous models like wolf and rabbits, and also the computation between wolves from mathematical biology. You can also implement and expand. All right, I think I'm cautious about time. We are almost reaching the end. I will finish my talk and open up for discussions in case you may have questions or any thoughts you want to share. And the time is yours.
Yes, thanks, Longzhu, for this high-level lecture. Species distribution modeling is a very well-known subject and used a lot in ecology modeling. And most of the time, we are dealing with a binary variable like presence, absence, but sometimes we also modeling the occurrence of a species. So in terms of number of species of a specific species per kilometer square, in terms of abundance of that animal. So over there, we can also use it regression models. So not only as treating as a presence absent, but also as a regression model in general, isn't it? In case we talk as a occurrence.
Yeah, yes, we can do that. I mean, if you go back to the general linear model framework, you just change your link function. There's also, some, I mean, I didn't go into great details. Actually, there's some mathematical convenience to use different kind of functions. We talk about logic, and there's also probit. So it looks similar in shape as logic, but there's a reason, mathematically to use another one, mostly because the mathematical convenience. So the probit model is pretty much the inverse function of the normal distribution. The shape is more or less looking like a logic, and it's almost similar, just deviate a little bit. If you want to look at the graph, you can Google it. It's called a probit. And that also has been used profoundly in species model, especially for presence and absence. And for the Boson distribution, there are also concern about this strong assumption about the variation and expectation in Boson model, where we expect the expectation and variation are identical, and sometimes it's not really realistic. So there are also some log normal or some other variations. But those are all case-by-case studies, so I didn't go into the particular instances. So I just want to give you a high-level overview of the options of the species model in the framework of a general linear model, including linear mixed model. And also I talk about this maximum entropy idea, where you only have a present data and you can go about the estimation of distribution function instead of the particular value of a probability function. So that's the main structure of data. I will try to type up what I had today in a format and upload, so you can see better in slides and in words, and then you have something in writing to correlate and refresh your memory what I've learned today. But everything, like I said, is about high level. On next Tuesday, we'll have some substantial case studies for the tree height.